All right, today we're going to talk about three-dimensional coordinate systems because I figure since we are doing things virtually here for a little bit, we'll have a little bit of fun today and learn about something that it just extends our vector lesson a little bit further, but is not a difficult concept to undertake, and it'll help you in college when you take three-space calculus. And a lot of times folks ask me about this and I don't have a lot of time to spend, but we're going to take some time to spend because it is a nice extension of what we've been working on. All right. So far, we have been talking about in pre-cal the two-dimensional coordinate system, which requires an x and a y, or you could label it some other variable, but it's typically x and y. And when we have a point on this plane, and I'm just putting it in the first quadrant, that'll be x comma y. And how do we get to this point on this graphically? We would go over x in this direction, and we go up y. And this would be our two dimensions. And we have quadrant 1, 2, 3, and 4 as we're used to. But then what happens if I add a third dimension? Well, I took the liberty of borrowing this from your book, and Drew had borrowed their picture to draw the XYZ plane. So we have an x-axis, a y-axis here, but on the three-dimensional coordinate system, we have an x, a y, and a z, and it follows the right-hand rule when graphing this, and you'll see that the x is coming out almost at a 45-degree angle here. That would be west of south, it would be west of south. And then the y is coming out this direction, and the x is going up this way. And they call it using the right hand rule because if you were to put your hand on the x-axis and you rotate towards the y, your thumb is going up, so the z is going up. And I know it's awkward, but so if you had your positive x-axis here and you rotated your y-axis here and you were using your right hand, then the z is pointing upward. And so this is the positive z-axis, this is a positive x-axis, this is a positive y-axis. Okay, and you would have your coordinate points, instead of having two numbers, you'd have an x component, a y component, and a z component of your point. And what's fascinating about this is that now I'm going to bring this up here. The XY plane that we're used to is now in an octant instead of a quadrant. So we had quadrant 1, 2, 3, and 4, and this is the quadrant where x and y are both positive. But in the octant, the first octant, this right here is quadrant 1 in this small gray area here. But the first octant is the space here where x, y, and z are all positive. So this would be quadrant 1 that we're used to if z was 0. This would be quadrant 2. This would be quadrant 3. And this would be quadrant 4. So we're looking down at the XY plane in a rotated fashion, which is a little bit strange to folks sometimes when you first think about it. But we still have an origin, and the first octant, second, third, fourth, and fifth, sixth, seventh, eighth underneath. So it's kind of cool. And how would we get to a point in space? Well, you would do the same thing. You'd go over x, over y, and then up z, then put you someplace in space here. Okay? So instead of quadrants, we have octants. And I've got it spelled right here, octant. O-C-T-A-N-T-S. All right, so let's move along. So let's talk about what we already know about two dimensions with points. Let's say I have a point, A and B. Let's say I have a point that's A. Whoops, I'm sorry. It always takes me a few minutes to get going here. So let's call this point A, and this is x sub 1, y sub 1. And I have a point B, which is x sub 2, y sub 2. And we know so far that we, in two dimensions, that we can find the distance between these points using the distance formula. And I like to go over really quickly where the distance formula came from. geometrically. So if I have a point, and I'll put A right here and a point B right here, and I want to know the distance between them, which is D here, I'm going to take and make a right angle here. And this is going to be, if this is x sub 1, y sub 1, and this is x sub 2, y sub 2, this distance here is going to be the difference in the x's. So it's going to be the bigger x, which would be x sub 2 minus x sub 1. And then this distance here is going to be the difference in the heights. So that would be y2 minus y1. And conveniently, I can say that x2 minus x1 quantity squared plus, which we're seeing right here, y2 minus y1 quantity squared has to equal d squared. Thus, the distance is the square root of those two squared. So this distance formula actually comes from Pythagoras, which is pretty cool. All right, and then we can also find the midpoint. And I'm sorry that this is a little bit faint. We can also find the midpoint. Well, how do we find the midpoint between 2 points? Well, you just average the x's and you average the y's. It's as easy as it is. And when you're averaging two numbers, you add them up, divide by 2, add them up by 2, divide by 2. So those are easy things that we already know how to do in 2D. The good news is we can extend this to 3 dimensions by using the same exact formula, except that we're going to tack on a z component at the very end. So it would be, and it doesn't matter if it's x1 or x2 subtracted here, because we're squaring it. It's going to be a positive number no matter what. But our book has it as x sub 1 minus x sub 2 squared plus y sub 1 minus y sub 2 squared plus z sub 1 minus z sub 2 squared, which is the difference in, right? And a good way to do this is delta x quantity squared plus delta y quantity squared plus delta z quantity squared. And I would just be consistent on, which point you're using first in that expression. And the same can be held true as just to extend the midpoint formula. So we're average the x's, average the y's, and average the z's. Really simple to do. So let's do just a couple of quick examples. Okay, so we're going to give you 2 points. We're going to say given P, we'll use P instead of A and B, is 1, 2, 3, and Q, point Q is, well, what do you suppose we should make it? Yeah, let's just be boring and go 4, 5, 6. Nice and sequential. So our first example will be, we'll find the distance between these 2 points. So the distance between P and Q. Well, how do we do that? Well, we know the distance is equal to the square root of the distance between the change in x's squared, change in y squared, plus the change in z squared, all added together, square rooted. So I'm going to do 4 minus 1 quantity squared, that's the change in x's, plus 5 minus 2 quantity squared, plus the change in z's, which would be 6 minus 3 quantity squared. And so the distance is going to be, this is going to be the square root of, well, that's 3 squared, 3 squared, 3 squared. So that's going to be 9 plus 9 plus 9, which happens to be the square root of 27, which is 3 root 3. We'll just put units on here because that's what the distance would be, whatever units you're in. All right, well, let's go on part B and let's get wild and crazy and find the midpoint between these. So how do you find the midpoint between P and Q? Well, we just average the x's and average the y's. So the first step would be 4 plus 1 over 2. And then we would say 5 plus 2 over 2. And then we would say 6 plus 3 over 2. And so our midpoint, if we were to simplify, would be 5 over 2, 7 over 2, and 9 over 2. All right, now what I wanted to do was show you this really cool program, and I have put a link already to this program in to Moodle, and it's just Geogebra 3D. And when you open Geogebra 3D, and you can log in under your Google, you hit login over here where my big purple A is, right here. You can log in under Google, and I've logged in. So you can save your work if you'd like to. But I'm going to just plot some points, and it's really easy to plot points here, okay? So in Google, Geogebra 3D, and Geogebra 3D is the best program that I have found to look at things spatially. Our calculators don't do it well yet because we don't have an Intel chip and all that fancy software. But we can do it on our Chromebook, and this is an application that's free. So, all right, so I'm going to plot the first point, which was 1, 2, 3, and you just type in 1, 2, 3. There we go. See? And they're labeling it A. Now I could change that label if I want to P. See there, I made it P. All right, and so let's do another point, and we'll say that is our 4, 5, 6. There's our point. And if I press enter, that's going to give me another A here, but I want to make that Q. And there's our point. And let's prove to ourselves then that our midpoint, I'll call it M in just a minute, our midpoint, what did we say it was? We said it was, and we can open this little typewriter thing down here, just for your future reference. We can say our first point is 5 divided by 2, comma, 7 divided by 2, comma, and 9 divided by 2. Oops, I'm sorry, I didn't hit the divide. Divided by 2. Press enter, and that's giving me point A, but I'm going to relabel it as M. And clearly, and believe it or not, I'm going to close this. You guys can see, right, that M is definitely between P and Q, and it looks like it's certainly halfway in the middle, which is really cool. All right, now, what I wanted to show you on GeoGebra really quickly is that the red axis here is the x-axis. And sometimes in GeoGebra, you have to reorient it so that you're looking at, this is the first quadrant here, or first octant. And then the green one is Y, and the blue one is Z, okay? And I like to reorient things this way all the time. So sometimes you got to go back and forth. But what's really nice is that you can use your mouse and look all over the place with GeoGebra. Sometimes I get challenged, grabbing things. But anyway, and if you click on these 3 dots here, you can change the settings on your points. Like I can make the midpoint any color I'd like. So let's make it neon green just to be fun. Close that, and then so you see my midpoint is neon green. But so that's kind of fun. So GeoGebra is a nice, easy program to use to be able to create, shapes in the 3D, 3 dimensions universe. So I'm going to keep that up, but let's go back to our work here. So 2D naturally extends to 3D by just adding the Z component to our distance formula and our midpoint formula. All right. Another easy extension from 2D to 3D are circles. Well, I haven't had the opportunity yet to show you how I derive the equation of a circle, but let's say our circle here has a center of HK. There it is, there's our center. And we have a point on the circle that's XY. Well, if I wanted to calculate the distance between them, and with any point on the circle, we know that those are all the same distance, which is pretty cool. So I'm going to call that same distance R instead of D. Well, that equals, using the distance formula, which we just referred to as simple old Pythagoras, that would be the square root of the difference in the x's, which would be x minus h quantity squared plus y minus k quantity squared. And then we can square this to get it in our standard graphing form, which would be x minus h quantity squared plus y minus k quantity squared equals r squared, right? And that's the formula we all know and love for circles. So this is our equation of a circle where the center is HK and the radius is R. But what happens is that we can extend this very easily to 3 dimensions. Well, I suppose, how do you do it? Well, let's say we have a sphere here, and I'm going to put the XY plane in here, or 3D axes in here. This is going to be Z popping up out of the center here. And then I'm going to have X popping out here, and then we'll have Y coming out at you here. So this is Y, and this is X, and this is Z, right? And this is the origin. But our center here is going to be H, comma, K, which we're used to, and then our book uses L, H, K, and L. I don't know why they use L, but they just use L, so we'll roll with it. And then a point, any point on the sphere, we can just call X, Y, Z in 3 space, which is nice. Now, I like to put a line through my Z's so they don't look like 2's. All right, so if I want to find the distance between the center and a point on the outside of the sphere, all we do is we use the distance formula. And instead of D, we'll use R equals, well, the change in X, which is X minus H quantity squared, Y minus K quantity squared, plus Z minus L quantity squared. All right, and that's going to give us, if we square everything, X minus H quantity squared plus Y minus K quantity squared plus Z minus 1. Minus L. The L's look like 1's. So I'm going to make it cursive. Quantity squared equals R squared. So what's the only difference between the equation of a circle and an equation of a sphere? Well, it is just the difference between adding a Z component to our thing here. So this will be equation of a sphere centered at H, K, and L with radius R. And I brought the expression from our book into my document here and into your document so you can see that expression. Okay, so hang on just a second. And all right, so let's do an example of our sphere in 3D. I happen to have one right here. And this first example says, let's write the equation of a sphere that has a center of -1, 5, 8, and a radius of root 5. So let's ignore my phone because I'm not going to take it right now. Of course, it's very loud. Never a dull moment. Here we go. Let's try it. Sorry about that. That's what happens when, we're in Virtualville. All right, so the center is -1, 5, and 8, as I just mentioned. And let's write that equation. It's really easy. It's going to be X plus 1 quantity squared plus Y minus 5 quantity squared plus Z minus 8 quantity squared equals root 5 squared is just 5. So there's our equation, which is pretty cool. Easy enough to write, just like it is with circles. Okay, so now we're going to go Geogebra, and we're going to actually plot these things. So I'm going to delete these little points out of here. And with Geogebra, you can actually just type in your equation. So we're going to type in X plus 1, and I'm going to put the square here. There's the square. Plus, parentheses, Y minus 5. Yes, and all sorts of cool 3D shapes are popping up, I see. Squared. Plus Z minus 8 squared equals 5. All right, you might be going, well, where is it? Well, here we go. I'm going to close this. And I'm going to bring this down. See, there it is. There's our sphere in space, in 3D space, which is really cool. It's like a piece of perfectly chewed bubble gum, you know, bubble. Well, it's pretty cool. So let's put the center in just to see what happens when I want to look at the center. The center we said was -1, 5, 8. And there it is. There's the center. Everybody see the center? Pretty neat. I can zoom in a little bit more here so we can see it on the screen. But yeah, there's our sphere. A radius √5 with a center of -1, 5, 8. So that's kind of fun. And in your homework, I'm going to want you to play with this Geogebra 3D calculator / grapher. And as I said, I put the link on Moodle so you can go ahead and play around with that. All right, moving right along here, because I'd like to be done as soon as possible, right? I picked this up from your book so that you would have an idea on how to graph things in 3 dimensions. And as I mentioned previously, the x-axis comes out at you this way, the positive x-axis. The y-axis comes out this direction, and the positive z-axis goes up, down. Okay, and not like this, because then you can't see the spatial part here. This is a little too tight here on the x-axis. It needs to be a little bit more rotated this way. Okay, when 2 lines in 3D space intersect, there's no, break in them. But if there's a line that's behind a line in 3D space, you break the line that's behind it. Same thing here. So you see how AB is behind CD. If you have a plane and you have a line going through the plane, what you do is you have the line going until it gets to the plane, and then when it's underneath the plane, it's dashed, and then when it comes back out again, it's solid. Okay, and this is the line that's above the plane. This is a line that is in the plane. So this is a line that is this one is actually below the plane. But let's say if it was going in the plane, you would have it go in and hit the line, hit the plane like that, and then it would go through and then hit out on the other side. That's how you would draw it, which is kind of cool. And I'm going to be honest with you, 3D space drawing is not one of my fortes, but it's fun to try. All right, well, this would be a sphere, and you can see the outer edge of the great circle, and then this would be the inside of the circle that's on the inside of the sphere. So that's dashed, and the same thing here with it on the X, Y, Z coordinate plane. All right, I just wanted to show you that. I thought that was a good kind of a demonstration on how to graph things by hand. Okay, now what's interesting about 3 space is that we know what a line looks like in 2 space. And I have a nice equation here in my mind here. It's the one I want to maybe illustrate this with is, let's say I have a line in standard form, which would be 2x plus 4y equals 8. And this is what I call standard form, but it's also intercept form. And that's when I taught Algebra 1. Now, why do I call it intercept form? Well, because if I let x equal 0, we can figure out what y is. When x equals 0, I'm going to cover this point up here. When x equals 0, y is 2. Okay, and then I can find the other intercept by saying, let's let y equal 0, and then we get x equals, if I let y equal 0, I get x equals 4. And then I could take the xy plane here and go 1, 2, 3, 4. I know it's not uniform. And 1, 2 right here. And using the intercepts, I can actually graph my line, which isn't very straight, but yes, it's got a wiggle in the middle. So there's my line in intercept form. But in 3 space, what happens is when we have ax plus by plus cz plus d equals 0 instead of ax plus by equals c, and we have linear terms for the x, the y, and the z, this becomes a plane, okay, which is really pretty cool. that it's a plane. And we're going to play around with this a little bit. All right, so let's do an example. My example is going to be really simple. It's going to be x plus y plus z, and we're going to let d equal 0. Well, no, we'll go minus 1 equals 0. That's a more interesting line. Okay, well, what happens when I let x and y equal 0? So we're going to find the intercepts. When x equals 0 and y equals 0, what do we get? Well, we get z minus 1 equals 0, which is z equals 1. So this is the z-intercept. So to find the intercepts on a plane, you're going to have to let two of the coordinates equal 0. So then I did xy. Let's let y equal 0 and z equal 0. And what does that mean? Well, x minus 1 equals 0, which is x equals 1, which that's the x-intercept. And then how would I find the y-intercept? Well, I'm going to let x equal 0 then and z equal 0. And then my equation is going to be y minus 1 equals 0 or y equals 1. So all of my intercepts are 1. And I'd write the z-intercept at like this point here, 0, 0, 1. And then the x-intercept would be 1, 0, 0. And the y-intercept would be 0, 1, 0. Okay? All right, so let's go to our Geogebra. And let's delete these and we'll graph them. Or we'll graph our plane, which is x plus y plus z minus 1 equals 0. And there's our plane. Now notice that it's cutting through, the 2D space, which is the gray. And you notice that it cuts through the xy plane and it's forming the equation of a line. Well, that's because when z equals 0, if you in your mind cover up z here, I'm going to cover it up with the mouse, you get x plus y minus 1 equals 0, which is y equals negative x plus 1, which is the line that you see on the gray part here, this is that line right here, which is pretty cool. And if I were going to plot the intercepts, which we'll do, we'll say my first point was 1, 0, 0. That's the x-intercept. And then we'll plot another point, which was the y-intercept, 0, 1, 0. And then we'll do the z-intercept, which is the next point, which would be 0, 0, 1. And if you see that's, oops, sorry, I'm a little challenged spatially sometimes. Try to get it back so I can see it. The z-axis is right up at us here. Thanks. I don't know. Am I going to be able to get it back? Here, let's try this. I'm going to undo 50 million times here. How's that? There we go. So I have the x pointing out me here. That's what I wanted to show you, though. But you see how there's a triangular piece. I'm going to use my mouse here, right here. Those are the intercepts right here. But that shows you the triangular part of the plane, which is pretty cool. Okay. All right. Now let's talk about some other kind of planes. What happens if in this equation that I have right here, I change it to x equals 1. Let's see what that looks like. That means x is always 1. We'll hide these for now. So I'm going to type in x equals 1. Well, what is that? That looks like a plane where x is always 1. And do you see how it is perpendicular? Oops, I got to be careful. It's perpendicular. Oop, I did it again. Okay. I got rid of my... It's perpendicular. If I can do this correctly, we'll try. I'm telling you, I'm frustrated with this sometimes. I need to go the other direction. There we go. X equals 1. It's hilarious because I don't do video games, so I'm not very good at moving the mouse like some of you all are. But I wanted to show you that as you see how it's perpendicular to the z-axis. So x is, when you have x equals, it's perpendicular to the z, I'm not perpendicular, excuse me, parallel to the z-axis. And it's perpendicular to the x-axis, but it's parallel to the z-axis, and it's also parallel to the y-axis. I can get my letters all straight here, okay? All right, what about, let's see if we have y equals 1. Y equals 1. I promise to get my language right here. And I'm going to make this a different color. Let's make this different color settings. Color. Make it green. Okay. So the green one is y equals 1. So what do we suspect? It's going to be parallel then to the x and the z. To the x and the z. There it is. It's parallel to the x and the z, but perpendicular to the y. Yep. And then what if we let z equal 1? And we'll change that color because we can. I'm going to make it yellow if we can see that. Let's see. All right. This one's going to be then perpendicular to the z, but parallel to the x and the y. And I hope you can see that the yellow one is parallel both to the x and the y, or the xy plane, which is pretty cool, I think. And where all three intersect is an interesting point here. They intersect at the point 1, 1, 1. So the intersection of three planes like that is a point, which is pretty cool. That are perpendicular to each other. All right, pretty cool. All right, moving right along, because you'd like this to be done, I'm sure. So let's say we didn't have our nice cool grapher, and I asked you to sketch a graph of this plane. And I know it's a plane because all of these are degree 1, and it's got 3 space written all over it, so it's a plane. So let's use the intercept method. And if we had 2D space, what we would do is we'd let x equal 0, and then we'd let y equal 0. But since we're in 3D space, we're going to let x equal 0 and y equal 0, which is going to give me the equation 20z equals 60, which means z will be 3. So the z-intercept is going to be 0, 0, 3. Okay. What about the other intercept? We're going to let x equal 0, then we'll let z equal 0, which means I'm going to say that 15y equals 60 and y equals 4. So that point's going to be 0, 4, 0, and that's the y-intercept. And then lastly, we'll let y and z equal 0. So y equals 0 and z equals 0. And that means that the 12x will equal 60. And x equals 5. And then the x-intercept of this plane is going to be 5, 0, 0. And if I were to graph this by hand, I would do my z-axis first. My little arrow's a little bit weird. Okay, my z-axis first. And then I'd have the x-axis coming out here and the y-axis going out here. And then I'd go 1, 2, 3 in the z, 1, 2, 3, 4, 5 in the positive x-axis, and then 1, 2, 3, 4 in the y-axis. So this is x, y, and z. And then these 3 points would be the triangle part of the plane that's, is like extending through, extending through the XY plane. I'm a terrible 3D artist, but hopefully you get the point, and you will when I do it right now on Geogebra. All right, so I'm going to get rid of this one, and this one, and we're going to put our new one in there, which was 12x plus 15y plus 20z equals 60. And sure enough, let's plot our points to make sure we're right with our triangular area there. We said our points were first 0, 0, 3. And then we had the point 0, parentheses 0, 4, 0. That's our second point. And then we had 5, 0, 0. And there we go. And if you can see, if I can do it accurately without messing it up again, that's the triangular area that we were able to graph, and it's going through space, intersecting our x, y, and z axes through those points, which is really neat. Okay? All right, last, let's talk about vectors, because that's what our topic was originally. Well, what do we know about vectors in 2 space? Well, we know that vectors in 2 space, and I got this from your book, that we have the head minus tail rule, which I like to call the tip. So if I want to do component form, and I have 2 vectors, what do? We take the tip minus the tail. So this is going to be x of the tip minus x of the tail, comma, y of the tip minus y of the tail, and that would be the component part of our vector, which is basically the change in x, comma, change in y. And then the magnitude, we all remember, and the book only uses single bars, I like to use double bars, is the square root of delta x squared plus delta y squared, which is your component part squared. And then we can add them and subtract them, which we know how to do. We can find the dot product, which is where we multiply the x components and then add them to the y components. And remembering that the dot product, if it's positive, we have an acute angle between the 2 vectors. If the dot product is negative, we have an obtuse angle between the 2 vectors. And if the dot product is equal to 0, we know our vectors are orthogonal or perpendicular to each other. And, we proved these properties of the vectors in 2 space. And I'm not going to go over that again, but that's what we know so far. And we know that the angle between 2 vectors is the inverse tangent of alpha, right? We want to find alpha, which is the inverse tangent of the y component over the x component. And we do that so we find alpha first if we're not in the first quadrant. So we remember how to do that. All right. Now, how does this extend to vectors in 3D? Well, if you have the same magnitude in the direction, all these coordinates are going to be equal. You will have the same magnitude and direction if your coordinates are equal. The addition property, what do? We still add the x components together, the y components together, and the z components together. Subtraction, we would just add the opposite, which means you subtract the x components, subtract the y components, subtract the z components. Nothing's changed. The only difference is that we have now just added the z component to our calculations. And then the magnitude is the same, except that we add the z component. So this would be the x component squared, the y component squared, and the z component squared. Dot product is also the same, except that we've added the z components. We'd multiply the 2 x components, add them to the y components multiplied together, and then add them to the z components multiplied together. And then a unit vector is nothing more than the vector divided by its magnitude, where the magnitude is not 0. And in 3 space, we don't use angles as our way to dictate what direction is. We use unit vectors. So unit vectors give the direction in 3 space. Because angles are a little bit more difficult in 3 space. Okay? All right. So some of the homework's going to involve you doing this in 3 space, which is really very simple to do. So I know you guys can handle that. All right, last but not least, there is one other type of multiplication that does not apply in 2 space, but it applies in 3 dimensions. And it's called the cross product. And why this is an important thing to learn is that when you do the cross product, what happens is you cross 2 vectors together, and they call it the cross product because they're using the cross symbol for multiplication in between the 2 vectors to indicate that you're doing a cross product. The cross product result, so this isn't on here, the cross product result is a vector orthogonal or perpendicular to both u and v. So that's a unique geometric property, and I'll prove it with the dot product when we're done. Okay, so what we're going to do is we're going to use our old friend, the vectors. We're going to use u equals the vector 1, 2, 3, because that's easy, and v equal to, what do you guess? 4, 5, 6. And those are vectors in 3 space. And then the cross product, this is a big ornery formula to have to memorize, but I'm going to show you how to do it without having to memorize. So I'm going to write this down. So we're going to go u cross v is equal to, what you do is you set up like it looks like a matrix, and it is, with an I, j, and k component up in this first row, and then you put your first vector in the second row, which is 1, 2, 3, and then you put the second vector in row 2, which is 4, 5, and 6. Okay? And now, this is how you, and then what I'd like you to remember is that you're going to have to put a plus up here, a minus up here, and a plus, because when we're using the second row, the second column, we're going to put a negative in front of that calculation. All right, so this is how you do it. I am going to do the first row. So I'm going to put parentheses here, and then I cover up the components in the first column. And then I take 2 times 6, which happens to be 12. So I'm going to go down 2 times 6, and then I'm going to subtract going up. So that would be minus 15, because 5 times 3 is 15. And you'll see that this is u2, v3. So u2 times v3 minus v2 times v3. So we're going to multiply down, subtract going up. So that's going to be 12 minus 15, I, minus, now why am I using minus? Because this column here is the minus column. I'm going to take my finger and cover up the minus column. And then put parentheses here, and then we're going to do the same thing. We're going to multiply down, which is 6. And then we're going to subtract the multiplication going up, which is minus 12. I'm sorry. Yeah, so it's 6 minus 12, j, plus, because I'm using the plus column now. Here we go. I'm going to move my finger here, and then we're going to cover up the k column. And now we're going to multiply down, which is 5, and then subtract the multiplication going up, which is 8k. And you'll see that this works out to be the same formula. Okay, now let's simplify, and we get negative 3i minus, this is minus 6 minus 12, so this would be plus 6j, and then minus 3k. All right, now I can also write this vector as negative 3, 6, negative 3. All right, and this is U cross V. That's my vector V, okay? Now, how did I prove my statement up here that I said they were both perpendicular? Well, this is how I'm going to do it. This is my proof. I'm going to do the dot product of U cross V. So I'm going to go U dot U cross V. Okay, so what is U? Well, U is 1, 2, 3. And I'm going to dot it with U cross V, which we just figured out was -3, 6, -3. So what do we do when we do that? Well, we multiply the x's and we get -3, add it to the y's multiplied, plus 12. Wait a minute. Did I do that right? Yes. Minus 3 times minus 9. I was in a panic moment because I thought this was a 1 and I was going to be in really big trouble. And so no, what happened? We got 0. Therefore, orthogonal vectors. So U is orthogonal or perpendicular to U cross V, which is pretty cool. All right, let's do the same thing with V. So we're going to say V dot U cross V. So V was 4, 5, 6. And I'm going to dot it with U cross V, which we just figured out was -3, 6, -3. And so what happens when we multiply that out? We get 4 times 3, which is -12, 5 times 6, which is 30, minus 18. And guess what, folks? That also equals 0. Therefore, sorry, my therefore got a little bit weird there. My therefore, V is orthogonal to U cross V. So what did this multiplication yield? It yielded a vector, U cross V, it's -3, 6, -3, that was perpendicular to both U and V. And what's really cool about this property is in physics, you need it for torque because U cross V is the way that if you were going to screw something in with torque, the way that it's going to rotate. And that's I know that's a big amount there, but I also want to show you how to do vectors really quickly because it's kind of fun. We're all about having fun in this virtual reality that we're living in at the moment. Here we go. I'm going to go back to my Geogebra. Let me delete all these. If I could see them, I would not delete so many. Here, just pay attention. Just a few minutes more. I know I'm getting there. I'm deleting them all. I'm sure there's an easier way to delete them all, but there we go. Okay, so to do vectors, what we have to do is in 3 space, we have to do the vector command, vector, whoop, I can't type either, vector. And I'm going to use the one where we start and end at a point because I think that's easier. So we're going to start in standard, we'll put them in standard position, which means 0, 0, 0 is the tail, comma, and then the tip is going to be where it's pointing. And our first vector was 1, 2, 3, as I recall. 1, 2, 3. Right, to be boring, there's a picture of my first vector. Woohoo, I drew my first vector. All right, let's do another one. Vector. And then we're going to start at 0, 0, 0 in standard position. And then the tip is going to be at 4, 5, 5, 6. And there's the second vector. Okay, and they even call it U and V on there. So if I turn it around a little bit, you get to see U and V. Okay, and now I'm going to do the U cross V vector that we had. And we said that vector, parentheses, and we're going to put it in standard position, was 0, 0, 0. And then the terminal point, comma, or the tip was -3, 6, -3. Okay, so graphically, I have graphed all 3 vectors here. And right now, the way it looks, you can't really see that it's perpendicular. So I'm going to turn it a little bit. I know I'm challenged. But now, can you see that that looks like a perpendicular angle between these guys? And they are. It's perpendicular, which is really pretty cool. Okay, and it's showing you, right, that this one vector, -3, 6, -3, is below the plane, which is really kind of neat. And so I like being able to show that visually, that you can indeed see that these are perpendicular to the same vector, which is nice. I like playing around with these. Very, very cool. And anyway, I just thought it would be a little bit of fun to play with vectors, spheres, and planes, and just create some more fun finding distance and magnitudes of vectors and equations of circles and spheres and planes on these virtual days where we need to make some learning fun. So have fun with GeoGebra, play around with it a little bit, and you guys have a great rest of your day.